Welcome back, AI architecture enthusiasts. Today, we're diving into the revolutionary technology that powers ChatGPT, modern translation, and the most advanced AI systems of our time. If you've ever wondered how artificial intelligence can understand and generate human language so effectively, you're about to meet the transformer architecture. This breakthrough has fundamentally changed the landscape of AI, making possible the large language models we use every day. Get ready to uncover the architecture that changed AI forever, and see why transformers are at the heart of today's smartest machines. Before transformers, sequence processing in AI was dominated by RNNs and LSTMs. These models processed data one word at a time, making them slow and often struggling with long-range dependencies in language. In 2017, everything changed with the introduction of the "attention is all you need" paper. This new approach allowed models to process entire sequences in parallel and use attention mechanisms to understand context. This breakthrough paved the way for today's large language models, enabling them to handle complex language tasks with unprecedented efficiency and accuracy. RNNs faced a major bottleneck. They processed data word by word, making them slow and hard to train on long sequences. They also struggled to capture relationships between distant words. Transformers, on the other hand, process entire sequences at once, allowing every word to attend to every other word, no matter their position. This parallel processing makes transformers highly scalable and efficient on modern hardware. Their ability to handle long-range dependencies without degradation has enabled the creation of powerful models like GPT, BERT, and T5, which now power many of today's AI applications. The core innovation behind transformers is self-attention. This mechanism allows each word in a sequence to look at every other word and decide which ones are most relevant for understanding its meaning. Each word is represented by three vectors: query, key, and value. The model calculates attention scores to determine how much each word should attend to others, then creates a new representation using these scores. For example, in the sentence, "The animal didn't cross the street because it was too tired," the word "it" attends strongly to "animal" to resolve the reference. This ability to learn relationships automatically is what makes transformers so powerful. Imagine each word in a sentence having a spotlight it can shine on other words. This spotlight helps the model focus on the most important words for understanding context. For instance, when processing a sentence, the model can highlight connections between pronouns and their references, or between verbs and their subjects. This visualization helps us grasp how self-attention enables the model to capture complex relationships within language, making it adept at tasks like translation, summarization, and question answering. Single attention heads might focus on just one type of relationship in a sentence, but language is rich and multifaceted. That's why transformers use multi-head attention. By splitting attention into multiple heads, each can learn to focus on different patterns such as grammar, meaning, context, or relationships. These diverse perspectives are then combined, resulting in richer representations and more stable training. In modern models, it's common to use 8 to 16 attention heads, each acting like an expert analyzing a different aspect of the sentence. Think of multi-head attention as having a team of experts, each specializing in a different aspect of language. One might focus on grammar, another on meaning, a third on context, and yet another on relationships between words. By combining their insights, the transformer model can achieve a deeper and more nuanced understanding of language. This approach leads to better performance on complex tasks and ensures that the model captures a wide range of linguistic features. While self-attention is powerful, it treats all words equally, regardless of their position in the sequence. However, word order is crucial in language. To address this, transformers use positional encoding, which adds information about each word's position to its embedding. This allows the model to understand not just what each word is, but also where it appears in the sequence, preserving the structure and meaning of sentences. Positional encoding uses mathematical functions, specifically sine and cosine, at different frequencies to create a unique signature for each word's position. This signature is added to the word's embedding before processing. The result is that the model can easily learn relative positions and handle sequences longer than those seen during training. Some models even learn positional representations during training, offering flexibility for various tasks. The use of sine and cosine functions in positional encoding isn't arbitrary. These functions provide smooth, bounded values that make it easy for the model to learn relative positions between words. This mathematical approach ensures that the model can generalize to sequences of varying lengths and maintain a consistent understanding of word order, even in sentences it has never seen before. A full transformer model consists of two main parts, the encoder and the decoder. The encoder is responsible for understanding the input, while the decoder generates the output. Both parts use multi-head self-attention, feed-forward networks, residual connections, and layer normalization. These components are repeated multiple times, often 12 to 24 layers in modern models to build deep, powerful representations. This architecture is the backbone of many state-of-the-art AI systems. The encoder processes the input sequence by combining input embeddings with positional encoding, applying multi-head self-attention, and passing the result through feed-forward networks. This process is repeated across several layers. The decoder, on the other hand, generates the output sequence. It uses masked multi-head attention to prevent the model from cheating by looking ahead, and incorporates information from the encoder through encoder-decoder attention. This setup enables the model to generate coherent and contextually accurate outputs. Transformers rely on several key components to function effectively. Residual connections help with gradient flow during training, making it easier to train deep networks. Layer normalization stabilizes training, ensuring consistent performance. Feed-forward networks apply position-wise transformations, allowing the model to learn complex patterns. These elements work together to create a robust and flexible architecture, suitable for a wide range of AI tasks. Since their introduction, transformers have evolved into several variants, each tailored for specific tasks. BERT uses an encoder-only architecture for understanding language, making it ideal for search, classification, and question answering. The GPT series employs a decoder-only architecture for generating text, powering applications like ChatGPT. T5 frames all tasks as text-to-text, offering a unified approach to natural language processing. Vision transformers extend the architecture to images, achieving state-of-the-art results in computer vision. To address the computational demands of standard transformers, researchers have developed efficient variants. Linformer reduces attention complexity to linear, Performer uses kernel-based approximations, and Big Bird introduces sparse attention patterns. These innovations make it possible to train and deploy transformers on larger datasets and longer sequences, expanding their applicability across domains. Training a transformer model typically begins with a pre-training phase. During this stage, the model is trained on massive text corpora using self-supervised objectives. This allows the model to learn general language understanding without needing labeled data. Pre-training is computationally intensive, requiring significant resources, but it results in a model that can be fine-tuned for a wide range of specific tasks. After pre-training, transformers are fine-tuned on specific tasks with much less computation. Fine-tuning adapts the model to particular applications, such as sentiment analysis, translation, or question answering. This approach leverages transfer learning, allowing the model to quickly achieve high performance on new tasks with limited labeled data. Fine-tuning is a key reason for the widespread success of transformer-based models. One of the most remarkable findings in transformer research is the scaling law. As you increase the amount of data, the number of parameters, and the computational resources, model performance continues to improve. At large scales, transformers exhibit emergent ability skills that were not explicitly programmed but arise from the scale of training. However, this also brings economic and environmental considerations, as training large models requires significant energy and resources. Transformers have revolutionized natural language processing. They power machine translation, enabling accurate and fluent translations between languages. They excel at text generation and summarization, producing coherent and concise outputs. Question answering systems and sentiment analysis tools also benefit from transformer architectures, delivering high accuracy and reliability in real-world applications. Beyond language, transformers are making waves in code generation. Tools like GitHub Copilot use transformer models to complete code, explain snippets, and even detect bugs. These models assist developers by automating repetitive tasks and providing intelligent suggestions, making software development faster and more efficient. Transformers are not limited to text, they're also used in multimodal AI, which combines text with images, audio, and other data types. This enables applications like visual question answering, where a model can interpret an image and answer questions about it, or content generation that spans multiple modalities. Multimodal transformers are pushing the boundaries of what AI can achieve across different forms of data. Transformers are making significant contributions to scientific research. For example, AlphaFold uses transformer-based models to predict protein structures, revolutionizing biology. In drug discovery, transformers help identify promising compounds. They also assist in analyzing scientific papers, accelerating the pace of research and discovery across disciplines. In the business world, transformers are driving automation and innovation. They power customer service chatbots, automate content creation and marketing, and enable advanced data analysis and reporting. Process automation using transformers streamlines operations, reduces costs, and enhances decision-making, making businesses more competitive in the digital age. Transformers have become the foundational architecture for modern AI. Their attention mechanisms alone have achieved remarkable results across domains, from language to vision and beyond. While they are computationally demanding, their parallel nature, scalability, and effectiveness have made them the architecture of choice for most state-of-the-art AI systems today. Looking ahead, the future of transformers is bright. Researchers are working on more efficient attention mechanisms to reduce computational requirements. There's a strong focus on better multimodal integration, allowing models to seamlessly combine text, images, and audio. Improved reasoning capabilities and reduced energy consumption are also key goals, ensuring that transformers remain at the forefront of AI innovation. As transformer models grow larger and more powerful, their economic and environmental impact becomes increasingly important. Training massive models requires significant computational resources and energy, prompting the AI community to seek greener, more sustainable solutions. Balancing innovation with responsibility is a key challenge for the future of AI development. From virtual assistants to recommendation systems, transformers are now part of our daily lives. They help us communicate, find information, and automate routine tasks. Their ability to understand and generate human-like language has made them indispensable tools in both personal and professional settings, quietly powering many of the digital services we rely on. At the heart of the transformer's success is the attention mechanism. By allowing models to focus on the most relevant parts of the input, attention enables deep understanding and flexible reasoning. This simple yet powerful idea has transformed not just AI research, but also the way we interact with technology, making our digital experiences smarter and more intuitive. To sum up, transformers have revolutionized AI by introducing parallel processing, self-attention, and scalable architectures. They have enabled breakthroughs in language, vision, code, and beyond. As research continues, we can expect even more efficient, capable, and responsible AI systems, all built on the foundation of transformer technology. Thank you for joining us on this deep dive into transformer architecture. We hope you now have a clearer understanding of how transformers power modern AI and why attention really is all you need. Stay tuned for more explorations into the engines of modern AI, and remember, the future of artificial intelligence is being built today, one transformer at a time.